a ring here on the xy plane. So the ring would look like something, some oval object if you place in the xy field like this. So this is the xy plane. And you have placed a ring, and this ring is suppose lying on this axis. So for simplicity, why don't we make this as an axis here itself? From the center of the ring, we can make the axis in this way. Suppose we make it like this, x, right? And if it is lying in xy, let's make it in this way. It's lying in xy. So this is xy plane, and we have z-axis in this way. So this is the kind of diagram we can try to imagine, that you have a ring which is placed on the xy plane, and this ring is a charged ring, right? It is a charged ring with a positive value q, the total charge, and we have placed like this, and the z-axis is passing right through its center, perpendicular to this, right? It's perpendicular to this. So we can just make dotted line to indicate this. So this is the center R, and suppose the radius is R. The radius is R of this ring, capital R. And we are interested here to find this electric field which is at P, and this is at a distance, suppose Z, from the plane xy. So we have xy plane here. Try to imagine this flat xy plane like this, okay, and the z-axis is like this. So this is placed on xy plane, which is lying on a floor, suppose, and we are interested to find at z point from the center, from the origin to this point P, which is at z distance. At this point, because of this charged ring, what is the net electric field at point P? We'll try to use calculus to figure out what is the net electric field. So what we know about until now is the radius of this ring is R, and the distance of P from this origin point 0, 0, 0 is, origin is O. From this point it is at a distance Z, and somewhere here we'll denote what is the elemental portion of this ring that we have taken. Now, quite interesting part here is, this is a round, so this is the arc. We will consider this to be a differential element S, right? Differential element, elemental part of this ring, which is suppose ds. It is linear, and the distance between this and this is important. So we'll draw this line showing that it is connecting this elemental ds, elemental part of this ring, which is on the ring, and this is connecting to the point of interest P, and suppose we say this is small r. So this R, if you use the Pythagoras, right? So this radius with the center is going to make 90 degrees. This is Z and this is R. So this is hypotenuse. So this is going to be equal to under root R square plus Z square. This is what the arrangement we have. And now we'll try to figure out. So the total charge in the ring, the total charge in the ring is Q. Radius is R. Radius is R. Okay. So these things are given. Well, it's also uniformly distributed. So this ring is uniform and this charge is uniformly distributed. So this is a positive charge and this is uniformly distributed. So one thing is clear, that if this is the situation, then because of this elemental part of this ring, charge part of the ring, the direction of this elemental electric field would be in this direction. And suppose this is making, so let me increase this length, this is Z axis. Suppose this length, this angle is theta degrees. This is theta. If this is theta, then by geometry we know that this should also be theta. Okay. Well, so let's understand the geometry again. We have placed this on the xy plane. The axis, Z axis, is passing exactly through the center. And we are interested to find the electric field, net electric field at point P, which is at any point, at a distance Z, it is lying at a distance Z on the axis of this this ring. And this ring has a radius R. And we are interested to find what is the net electric field at point P. So we have taken the elemental part of this ring as ds, and now we'll be figuring it out. If the total charge is Q and the length, we know if R is what is the radius, the length is going to be 2 pi R. So we can write this here somewhere, that this linear charge lambda would be equal to net charge Q by 2 pi R, right? This is going to be the lambda, which is linear charge density. And this linear charge density would be equal to, so this is ds, right? So this ds is the value here. So dq is the charge which is in ds. So dq by ds is equal to lambda. Therefore, what is dq? dq is equal to lambda ds. Okay, so these things we know here, and then we'll try to figure out what is, because of this elemental, dE is the differential form of the electric field, elemental electric field, because of ds. Now think over it. If you take just the counterpart of it, somewhere here the elemental, it would be in this direction, right? If you take any part, it would be in this direction. But we need to see that if you go in and around every, say, if you imagine this from the whole perspective of the ring going around, taking one round, you would find that this would be lying in this plane, somewhere in the plane which is Z and X axis, and making an angle theta. Why? Because all the values are going to be same. Everything is going to be same. However, if you figure it out symmetrically, if you go the other way, all the components which would be perpendicular to this plane, right? they will be cancelling out each other perpendicularly. Vectorally, they'll be cancelling out each other, and the net of all those elemental DE, when you add up, then the net DE would be all along this direction. The component which is parallel to this z-axis is going to add up. If you consider all the elemental in and around the entire ring, you would find if you have elemental here, it's going to be here. And then if you resolve this DE into corresponding components, one would be parallel to this theta, one would be the z-axis, the other would be perpendicular. The perpendicular ones are going to cancel out each other, right? If it would be plus sine theta, it would be minus sine theta, and it's going to cancel it out vectorally. But what's going to add up? Look carefully. It's going to add up this way, and this component of DE which is going to add up is going to be DE cos theta, right? DE cos theta, if you take the magnitude of this. So DE cos theta, so the net elemental DE net is going to be equal to magnitude of DE cos theta. Why? Because this component of this DE, which is lying in the plane, is going to add up if you go around this ring. However, in going around this, the perpendicular component is going to vectorially cancel out each other. So the net is going to just be in this direction for all. So for all those, we have to write that the net DE should be equal to DE cos theta. So just from the geometry, we are able to deduce these aspects, which is very important. So firstly, we'll figure it out what is DE. So this DE, the magnitude of this DE is going to be equal to, this magnitude is going to be equal to 1 over 4 pi epsilon naught dq, which is dq is lambda ds divided by, and what is the distance, right? So this distance is r squared plus z squared, this r squared, so it comes out to be r squared plus z squared. This is going to be this value. Now DE cos theta, all right. So if you want to find this magnitude of this, so it comes out to be, therefore, DE net value is whatever DE we have got, which is 1 over 4 pi epsilon naught lambda ds over r square plus z square, all right, and then cos theta, right? So cos theta. So cos theta is going to be, from the geometry you find that if this is theta, this is the vertically opposite angle theta, and this comes out to be base, which is z over hypotenuse. So this cos theta could be written as, therefore we'll get DE net is equal to 1 over 4 pi epsilon naught lambda ds over r square plus z square times cos theta is z divided by this hypotenuse value, which is under root r square plus z square. So this is what we get as the magnitude of the net electric field. Well, so I'll have to rub this to find the space to continue with the final expression. Now this is 1 by 2 and this is 1, so let's simplify a bit. So we'll get 1 over 4 pi epsilon naught. This comes out to be lambda ds over, it comes out to be r square plus z square whole raised to the power 3 by 2. So this is 1 by 2 plus this, it comes out to be 3 by 2. So therefore, net electric field E net is equal to integration of this. Therefore, E net is equal to, take out all those things constant. So this is constant, everything is constant. So we'll take out the constant out of integration sign. So this is lambda, and this comes out to be r square plus z square whole raised to the power 3 by 2 times, and then we have just ds. So ds is that elemental value length. If you go around, it's going to be 2 pi r. So if you integrate over this, the entire ring of radius r, so this, therefore this comes out to be E net as 1 over 4 pi epsilon naught times lambda. Now lambda we have already written there, right? It is q divided by 2 pi r times 1 over r square plus z square whole raised to the power 3 by 2, and this comes out to be times 2 pi r. So here 2 pi r and 2 pi r, entire thing gets cancelled out, and we are getting therefore E net as 1 over 4 pi epsilon naught q divided by r square, and q over z was also there, right? Here z is also there. So let us just include this z here, because z divided by under root, it was there. So let this be z. Here we'll include the z, and we have z r square plus z square 3 by 2. So this is the final expression we are getting. This final expression that we are getting is E net is equal to 1 over 4 pi epsilon naught qz by r square plus z square whole raised to the power 3 by 2. Take down, it's extremely important to understand the step by step and the approach, how we have used the calculus to figure it out. Well, now here also, if you are going to approximate, suppose the radius, if you compare with the distance z, and if you remember, the z was the distance from the center of the ring to that point P, right? On the axis, z axis. So if you consider z to be very much big, larger in value as compared to the radius of the ring, then we can make that approximation. We'll come up with a different value then, right? So let me just rub this portion here to approximate this to a situation if you get z greater than, very much greater than r. So if z is very much larger than r, then our E net value, which is the magnitude of this, is going to be equal to 1 over 4 pi epsilon naught times q. Now we can make this r0 here, right? So we'll be left with z, and in the denominator it's going to be zq. So 1z and this would be cancelled out, and finally we'll get this approximated value as E net. Magnitude of E net, we already know what is the direction. It's along the z axis, which is k cap, is equal to 1 over 4 pi epsilon naught q over z squared. Now this again is the expression of a point charge, right? So if you consider this approximation, then this ring that we have considered could be reasonably considered to be a point charge, and we know this is the expression for the point charge when we have z quite far off as compared to the radius of the ring. So we have taken two situations of linearly charged density situation wherein the body we have taken to be a linear one, and then we try to employ calculus to figure out what is the net electric field at any point P along the distance as per the situation given. In the next, we can take another kind of object. Suppose we will take a disk, and then we'll figure out, because of this disk, which is a two-dimensional object, because of this, then how would we approach and use the calculus to figure out what is the net electric field at any point on the axis of this disk. So watch the next video